Okay, so if you watched part one, then you know we talked about all the different things that you need to do to set up a tune properly, to take full advantage of the capabilities of your computer in the car, the car's OS, and the HPTuner software. Basically, we're setting up a naturally aspirated vehicle to run open loop, and using a volumetric efficiency table that's been upgraded and all that stuff. And we went through the main menu items, or the main categories here on the scan tool that you need to set up. And now we're going to go into further detail on exactly which PIDs you need to log and how you need to set up the variables in each of these graphs so that you're logging everything correctly. And don't forget, if you subscribe to my channel, you can get access to all of the resources that I'm using here, like the layout that I've got here. I can just provide that in a simple file, or any of the Excel resources that I'm working with to manipulate the data later, that sort of thing. So let's go through these menus one at a time, and as we go through each of them, we'll discuss the parameters that are being logged and what you need to include in your PID list, which is actually this list over here on the left. This is where you would add each of the PIDs that need to be logged. You add each channel one at a time, and then the graphs must utilize whatever's in here. You can't use something that doesn't exist in this list. So let's just go through the graphs and we'll see what we need. So right click on the graph area, go to graphs layout. Now you'll see on the left hand side here each of the graphs that we just saw a moment ago. And up at the top, this tells you what is going to show up inside these cells. It shows you what you're actually logging, not the axes, but what's actually being logged. So in this case, we've got Spark Advanced Sensor. So Spark Advanced Sensor is, well, let me just, okay. So Spark Advance, if you just type it into the field up here, it'll autocomplete and show you where it is. Every car should support this, so just pick it out of the list, double click on it, and it needs to go here. And it needs to also be in this list over here. Somewhere I should see it. Timing Advance, I think is what it's called over here. I'm just going to expand this menu a bit. Yeah, Timing Advance, and notice how it says SAE in brackets. Anything that says SAE stands for Society of Automotive Engineering, means that parameter, that PID, is universally supported. It has to be supported. It's kind of like standardized, like USB or something. So anytime you see that, you'll know with confidence that it'll be supported. So you don't have to worry about whether your car supports it or not. So I guess one thing to keep in mind is that the nomenclature that they use here versus what's in this graph may not be exactly the same. You saw here it says Timing Advance, and in the graphs layout it said Spark Advanced Sensor. So I'm sorry about that, but it's not my fault. It's just the way HPTuners did it. You can blame them. But basically you just have to try to figure out what PID is being logged here and what it's called in here. If you don't get it the first time, you can keep trying until you get it. It's unfortunate how they don't keep the wording the same. And sometimes when you pick something, it'll ask you, like, are you sure? And yeah, so like you pick this. Well, actually, I got to pick something that's different. So just to show you, for example, let me just pick. Okay, I accidentally double clicked on something, but here, this is the window that you'll get every time you pick a new parameter. It'll say, like, the parameter that you picked is engine RPM, and the generic sensor responsible for that is engine speed. Do you wish to use engine RPM or engine speed? No, I know what I'm doing, or yes, sounds good. Like, this is the kind of confusing nonsense that I hate. generally speaking, you should go with I know what I'm doing and see if that works, because hopefully your judgment is sound. But if it doesn't work, then yes, sounds good might be more likely to work. So you can give both a try, really. But end of the day, you just want to make sure that what you pick is actually being logged in the PID list on the left. So we've got Spark Advance being logged. Engine speed sensor is RPM basically, and Manifold absolute pressure sensor is your map sensor, which is in my charts it's going down the left column here. That's what this is. So the first three charts, Spark, Retard, and MAF, actually the first four charts, all of these ones up to Wideband O2, they all have the same entries in the column axis and row axis fields. So, once you pick engine speed and manifold pressure, I think it'll pick the unit for you correctly. If it doesn't, then you can just select RPM and kilopascals. But you're going to have to type this part in on your own. And this is basically just, I don't like the way they do it here either. This is kind of weird, but it's basically every entry. So, every column that you have to enter all of the entries from 400 RPM all the way up to 8,000. And you put a space in between them, not a comma, not a hyphen or anything that you would normally expect. Just a space, apparently, is what they want. And sometimes that even doesn't work, but you'll have to fiddle with this a little bit. Or you like I said, you could just download my or I'll give you my layout file, and then you won't have to do this. But if you were to do it by hand, just copy this formatting, just put the numbers with spaces in between them, and it should show up on the graph. Same thing with the pressure. And then once you've got one of these charts good, then what you can do is you can just highlight, select the entire row, right click, copy it, and then for the next chart, like the KR, the knock retard, you can just put your cursor here, right click, and paste everything, right? So that way you don't have to type it over and over again. But basically, like I said, the Spark, the retard, the MAF, the MAF doesn't have the same format. The MAF is a one-dimensional table, so forget that I said that. The Spark, the retard, and the Wideband O2, they all have the same column and row axes. And they're okay. So the Spark one is measuring Spark Advanced Sensor. The KR is measuring knock retard. So just type knock retard, and it's this one up here. Just hit that, and then that's in degrees. You can specify how many decimals you want right here. Usually 1 decimal is good. And then down here you can also define your color coding. So if you want to pick like red and blue, for example, blue being good, red being bad, or sometimes I pick like blue meaning lean, red meaning rich. You can just sort of define what values are going to correspond to that color, and it'll blend the colors in between, so you get a nice gradient showing you visually how the data looks, right? So in this case, it's knock retard for the sensor that you're picking up on. That's the only difference between that table and the Spark table. And then going down to Wideband O2, this one here, it says user math 1, which means that it's a mathematical equation that the user had to enter. And that's because, as I mentioned in the first video, the Wideband O2 sensor only reports voltage, which doesn't mean anything to a person. So in order for it to mean something, you have to use a transfer function to translate that voltage into an AFR value. So to do that, you have to go to Tools and then Math Parameters. And then down at the bottom here, it says Maths User. So you can pick any of these functions. Doesn't matter. They're all like for you to use for whatever you want. So you just pick one, and then you got to go down here where it says expression, and you got to put your transfer function in. Now, the transfer function, you know, it's not that much different than the way you would normally express math in a computer language. You know, multiplication is like the asterisk symbol, division is like the slash symbol, plus minus, pretty self-explanatory. The only part that you would need to worry about is this part here. This is the PID like serial number, so that the HPTuner software knows which PID you're referring to, because it doesn't use words, it uses this code. In this case, 30,001.10. You don't need to know this, you just need to go to new variable. So whenever you want to insert this, so for example, I would type 2.375 asterisk, and then right at this point here where my cursor is now, then I'd click on new variable, go to parameter, click to insert or change. It brings up the same menu as it did before, and you just type, MPVI. Okay, so MPVI means your analog to digital channels. And like I said before, if you bought the HPTuner Pro hardware, it's going to have this green terminal block on it where you can plug wires into it, and that's for external sensors. So the Wideband O2 sensor is an external sensor, so it's going to belong to one of these channels. You have to pretty much guess which one it is. I mean, I think the terminal block actually has the channels numbered. So if you plug it in the one that says 1 on it, chances are it's going to end up being 1 in here, but just play with it until you get the right one. Double click on that, and it'll put this PID code in, and then, you know, finish off your transfer function, and then just exit out of this, and remember which function you assigned it to. So in this case it was user math 1, right? So that means that back in the graphs layout under wideband, you know, when you go to parameter, you know, you pick, or, you know, what you can do is you can just scroll down to the bottom here, and it says maths, user defined, and it's got user math 1 right here. So you just pick that one, and there you go. Like I said, you know, fill out your colors if you want to. Here's a part that I need to spend some time explaining. Let me just check to make sure I haven't glossed over anything else. Actually, so I've applied the same filtering to several tables. So let me explain what these filters are for. So the filter field is designed to limit the amount of data that is recorded. So for example, if you're recording, you know, once per second, after 10 seconds you'll have 10 data points. Some of the data points are going to be at different loading conditions of the car, different RPMs, different manifold pressures, whatever. You may not want to collect all of that data. You might find that some of the data is kind of like contamination. It's data that you don't want. So this is the feature that allows you to filter out some of the unwanted data. Now in the case of these tables like spark, retard, and wideband O2, that's the reason why I've got these filters on here, is because this is the stuff that depends on manifold pressure and RPM. So basically it depends on the load point of the car, right? So I don't want all load points to be recorded, and here's why. Normally when you are recording air fuel data, you want it to be during a phase of acceleration, or, you know, something that involves you actively putting power into the car. If you're decelerating, your foot's off the gas pedal and the car is slowing down, that's contaminated data that's going to screw up your calculations. And most of the time, I would say most users are not considering that. Most users are probably allowing that data to mix with the rest of their scan, and it's contaminating their results. They're probably getting choppy correction factors that produce a lot of unwanted noise on top of their readings, because it includes like the odd deceleration point that you didn't want in there. Now the reason you don't want deceleration in there is because when the car's decelerating, usually the timing will retard. Like the computer will just retard the timing on its own, because when you take your foot off the gas pedal, it's implied that you want the car to slow itself down, you know, by itself, right? So reducing the timing will do that. So the car usually does that for you, drops it down to 20 degrees or something like that. And it also usually leans out the fuel mixture, because again, like, you don't need gas, you don't need to waste gas going into your cylinder when you don't want the car to accelerate. Even if you have your foot on the pedal like 5%, it's enough to keep the computer thinking that it's in acceleration mode, and it will continue to behave in sort of a linear way where the output is predictable and proportional to what you're applying as a driver, the amount of throttle that you're applying, for example. So pretty much there's a linear range that goes from like 5% throttle all the way up to 100. And you know, that's the data that you want. You don't want this deceleration data. And then there's another factor as well, which is basically that even if you take your foot off the gas, there's probably a brief period of time where the engine is still producing power before it winds down enough that it starts to actually decelerate or to brake. So there's a couple of factors involved. So here's the two filters that I applied. The first one, PID 2701.120, greater than 0. That means that the torque on the engine, or the power that the engine is making, has to be greater than 0. If the torque that the engine is making is negative, it means that it's decelerating. So I made that greater than 0 as one condition. So I applied it to spark because I don't want to pick up any spark values that are part of the decel range. Knock retard, I didn't apply it because I want to know when the car's knocking no matter what. Spark, I just didn't want to know that because sometimes you want to advance the spark based on how the car is performing. So that I wanted to filter that, but not the knock retard. Knock retard is more of a safety thing, so I just wanted to leave that one excluded. Mass airflow, like I said, we're not really going to use that for this open loop tuning, but I put it in there anyway. Wideband O2, definitely I put that in there. Temperature, I put it in there. Throttle, I put it in there. Flow capacity, I don't think I did. I guess I could have put it in there too. Maybe I'll fix that later. But in any case, I just wanted to take a small break to talk about that filtering thing, because filtering is very important to get good data. And if you don't have good data, then the entire exercise, the last 50 minutes of me talking are wasted. So make sure that you are collecting good quality data in addition to, you know, the different types of data, right? So where was I? So, you know, we already talked about the user math function. So you'll have to use your transfer function in there to get your AFR values. Put your filtering in. Temperature, user math 2. What did I do here? Let's take a look. Okay, I did quite a few things actually. So user math 2, let me see. Manifold absolute pressure greater than 94. This one here is engine coolant temperature greater than 85. And okay, so what I did here was basically I'm still recording the air-fuel ratio, no different than before. And like no different than the wideband O2 table. I'm still recording AFR values to put in these cells. The only difference is I applied some filtering in the actual equation. I didn't filter it on the main screen like I probably should have. Instead, I just incorporated it into the math formula here, which I didn't really need to do, but I did anyway. And also, I needed this function. I needed a math function regardless because I'm still recording AFR, which means I need the transfer function, and here it is. Just the only additional part is just that I put these conditions here. So when you're putting conditions here, you're basically just having these little bracketed if statements. That's what they basically are. You know, such and such greater than 94. That's an if statement. You put it in brackets, and then you multiply it by another if statement and another if statement. If all the if statements report true, true is represented by a binary 1. So everything inside of a bracket will basically be a 1. So you'll get 1 times 1 times 1 times this is your actual AFR value here. So all it does is keep the AFR value. If it reports a 0, then it just nulls it out, and you just don't get anything. But really, I'm just going to show you actually an example of why you shouldn't do this. If you do this, you're going to end up with zeros in your data. You don't want zeros in your data. You want anything that's garbage data to just be omitted altogether. So the problem with having zeros in your data is that the zeros will end up being averaged with the real data, and it'll screw up your data. So really, this is a mistake. So what I'm going to do later on, off screen or whatever, I'm just going to use math function 1, which is the math function that has just this piece in here that calculates the AFR value. And I'm going to get rid of all these conditionals here and move them to the filter part of the screen over here. So under temp, under filter, I'll just add the conditions that I had in that equation number 2. I'll just move the conditions to this field here, and that way I'll still get the effect of filtering out that bad data, but I won't have a bunch of zeros in my data. So there's that. And this one actually uses, in addition to sensor speed, it uses intake air temperature. So intake air temperature sensor is one of the PIDs you're going to need to log in Kelvin, and then you can type in whatever range you want. I just arbitrarily entered this range from 290 to 323. So the way Kelvin works is 273 Kelvin is 0 degrees Celsius. So whatever temperature you think that your intake air is going to reach. So if it's like winter time and it's minus 20 degrees outside, your intake temperature is usually warmer than the ambient temperature. It might reach something close to 0. If you want to be just careful and cover everything, just pick a range that's safe, like minus 10 degrees Celsius up to, I don't know, 50 or 60 degrees Celsius, and just add those numbers, minus 10 and 60 in the low and the high end. Add it to 273. So that would mean that your range would actually be from 263 up to whatever 273 plus 60 is. So that's like, I don't know, 353 or something. And then you just type those numbers into this field with spaces in between them. It's tedious, but that's how you have to do it. And what that will do is, you'll have them all show up. You'll have them all show up on this vertical axis here. You can later on you can pick these values here, copy them, put them in Excel, graph them, and you can see the trend of your fuel ratio with regards to temperature. For throttle is still got engine speed and manifold pressure, so nothing different there. Oh, sorry, I was looking at the wrong chart. My mistake. So it's throttle is still logging AFR, and it's still got the filters that we applied earlier, and it's got engine speed and this time throttle position sensor. And then finally for flow capacity is a one-dimensional table, so you don't have a row axis. You've only got a column axis, and it's measuring mass airflow sensor in hertz. And then you've got what you've got to do here is you've got to go into your HPTuners editor and go to your math calibration, which is under airflow, and copy the numbers that you see in this axis here, because these are the numbers that you want to line up your scan data with this table. So these headers, these column headers, that's exactly what you want to type into the scan tool in here. And you do that, and then all of the AFR values and, sorry, not the AFR values, the RPM values will show up under the corresponding frequencies. So that's pretty much how you set that up. Now there's some stuff that I'm logging that doesn't show up in the charts, which is normal, because there's certain things that you just scan by default anyway. So I want to go through that just to make sure that you're scanning everything that's important. Some of this stuff is not important, so I'll tell you when it's not important. I'm scanning engine RPM, vehicle speed. Well, okay, so engine RPM is very important because it's used in everything. You must scan that. Vehicle speed, I would recommend scanning it. For some reason, it's broken on my scan. I don't know why it doesn't work, but it doesn't. It's not totally necessary. Just useful information to know from looking at your scan whether you were on the highway or not, but you don't need it. Mass airflow sensor, not totally necessary for an open loop tune, but I would put it in there anyway, just so that all the tables work and you have some additional reference that will help you understand your car and how it's behaving. Engine coolant temperature, you always need that. That's important to have. Intake air temperature sensor, again, you need that, and I think it's one of the PIDs we're logging, so yes. Mass airflow SAE, so you don't need both. You don't need two mass airflow sensor PIDs. Pick the one that allows you to record the frequencies that the sensor is putting out. Sometimes mass airflow is represented in like grams per second, like grams of air per second. So it's a different unit. You don't want that. You want the one with frequency. So whichever of these gives you frequency, just use the correct one. Manifold absolute pressure, you need that, but for some reason it's blacked out. I know that it is recording correctly on my car, but not sure why it's blacked out like that. Maybe I've got another one somewhere else, so we'll just keep an eye out for that. Oh, here it is. Intake manifold absolute pressure, and it's an SAE as well. So I guess this one that I picked here initially just didn't work because it wasn't SAE supported, so you can delete that. Intake air temp, again, this is a duplicate of this one up here. I've got a lot of duplicates, I apologize, but you only need one, so just make sure that you get the right one that's got numbers that correspond to your graph. If you're using Kelvin, you want it to record in Kelvin, or if you want it to record in Fahrenheit, you can pick the one that records in Fahrenheit, no problem. Just make sure you pick the right one and you don't need the duplicates. Cylinder air mass, that's like how much air is going into the cylinder on each cycle. It's just one of those things that is good to know. It's good to log it, but you're not necessarily using it in the charts. So it's up to you if you want to keep that. Timing advance, that's your spark. So you need that for sure. Knock retard, you definitely need that. Fuel trim cell tells you what mode the car is in. If it's in decel, idle, light throttle, medium throttle, heavy throttle. Sometimes you can use this to filter your data instead of the way I did it, which is to filter by torque and throttle position. But I don't trust fuel trim cell because fuel trim cell basically breaks up the VE table into quadrants and numbers them. So if a cell falls in a certain RPM and manifold pressure range, it gets assigned a number. So it'll just cancel out every piece of data that goes into a certain area of the VE table. And I don't really want to do that because there's a chance that some of that data might be good. And there's a chance that bad data might fall in other parts of the table. So I'd rather just specify the parameters myself rather than let the computer decide what it thinks. Accelerator pedal position, you're going to need this to do your filtering. All of these ones here, most of them are redundant. You only need one of the throttle sensors. So just type throttle into the menu when you add the PID. By the way, to add a PID, sorry, I forgot to mention this. Pick an empty row like this, right click and go to add channel. It'll bring up this menu like you've seen before, and just type throttle in there. And then you can pick what type of throttle you want. So in addition to the accelerator pedal position, you just want a throttle value that's going to tell you what the actual plate angle is, or the plate angle percentage, whatever. It's got to be a percentage. That way you can correlate that back to your accelerator pedal and find out at what pedal position is it actually making a change in your throttle plate position. Going down the list, we've got EQ ratio. I don't need that to be there. That's another garbage item. Air fuel ratio commanded. That's what the computer thinks that the AFR is. That's what it's trying to achieve. So sometimes it's good to log that, because what you might want to do there is have a chart that has your commanded AFR and then another one with your actual AFR from your wideband, and then you can compare the two together and see how far off they are. That's normally the way you would tune, except in our case we're going to do something a little special. We're going to customize our own sort of matrix that's going to have all the desirable air-fuel ratios that we are going to design from scratch, and then we're going to use that to compare against the actual AFR. So this is kind of an optional thing too. Here's a few. These gray ones are attempts that I made to pick up the Wideband O2 sensor unsuccessfully. They have some built-in functions actually for certain devices like AEM wideband or other companies. I find they don't work. So MPVI A to D input 1, that doesn't specify any kind of product. It's just saying whatever's on channel 1, that's what I'm picking up. These ones, I think they have built-in transfer functions, but if they don't work, what good are they? So just pick up on the MPVI A to D channel that has your wideband on it, run that transfer function through the math, and then pick up that math function, and you'll be fine. Delivered engine torque. This is what I used to filter the results so that I wasn't getting garbage data that belonged to the decel phase. So delivered engine torque, you want that to be positive. You might pick a different number other than 0. If you want it to be like truly accelerating, you might pick a number that's like 10 foot-pounds or greater or something. But I just picked 0 because I wanted to pick up all data that wasn't, literally decelerating. Fuel system 1 status, I don't know what that's for. That shouldn't be there. Short-term fuel trim, long-term fuel trim. I think these are pretty much defaults. They're part of the default layout of HPT. Fuel trims are the way you would normally tune your car if you were using a closed loop system. You wouldn't be using wideband readings. You'd just be picking up the long-term fuel trims, for example, after driving your car for a long time, and then adjusting based on that. That's kind of like novice level tuning. That's where everyone starts, and that's where I started, and it's good for a while, but eventually you demand more from your car, and you're going to have to abandon this altogether and just go with open loop tuning, which doesn't use this stuff at all, because this is based on your built-in O2 sensors, and we've just turned all that stuff off. Fuel pressure is good to have if you're running any kind of boost, a turbo or a supercharger, because then you're worried about whether or not you're supplying adequate fuel, because you have to supply more than the stock amount of fuel. So if your fuel pressure drops during your watt run, that will indicate a fuel supply issue. Fuel tank level you don't need, alcohol percent you don't need. Control module voltage, kind of okay to have that, just if you're interested whether your battery is holding up, because voltage can affect the readings that you get, or it can affect your fuel pressure. Not really important, to be honest, but you can have it if you want. Absolute load SAE, I can't remember whether it was, where did I find it? Yeah, delivered engine torque or absolute load SAE. I can't remember which one I used to filter. I think it was delivered engine torque, but I could be wrong. So anyway, you can try either one. The absolute load is similar type of quantity to delivered engine torque. Both measure load on the car. And essentially, if there's less than 0 load on the car, it means that the car is decelerating. So you can use either of these parameters, whichever one works for you. This one's SAE, so I think it has to work. So maybe this is the one that I actually used. But setting that greater than 0 will help you keep that decel data out of your scan. Barometric pressure, just for interest's sake, tells you what the air pressure is outside. Ambient air temperature, again, same thing, just tells you what the temperature is outside. A lot of junk in here, actually, to be honest. I have it in here because at times I've wanted to know it, but really most of the important stuff we've already gone through. you know, just by looking at these charts. So now that you have all of the PIDs that you need, and of course if you had like a supercharged car, you'd probably want some additional PIDs to show you your boost levels and stuff, but we don't have that right now. So these are pretty much all the charts you need to start with, and now all you need to do is connect your equipment to your car. You plug in your OBD2, plug in your USB to your laptop, and connect your Wideband O2 sensor. That's very important. Don't forget to do that. Connect your Wideband O2 sensor. The two wires that come out of the wideband should be a signal wire and a ground wire. All of the channels on the HPTuners module all share a common ground. So all your grounds, if you have more than one device hooked into it, all of your grounds are going to be tied to the same pin on the terminal block, but the signal wires are going to go to different channels. So most of the time, I mean, I don't know anybody who's got more than one channel in use at any given time, and it's usually because they have a wideband, so this probably won't be an issue for you at all. Just hook up your signal wire to any of the numbers and just pick the corresponding number in the software until you get a recording here. In order to test to make sure that you've done everything properly, all you have to do is go up here, connect to vehicle, and when you do that, then you won't see a change right away. A window will come up and it'll read the computer and it'll determine all of the supported functions that the car supports, but it won't actually show you anything. So in order for you to see that everything is working, you have to actually click on the start scanning button up here, the red button, and that will actually start recording the values, and you'll start to see them show up on the table. So then you just want to click through each of the tables to make sure that values are actually showing up on the screen. You might have to scroll a little bit in some cases to see the values, but make sure that they're all working properly before you take off in your car. Usually what I would do is start scanning, check every graph to make sure that they're all recording properly, check your PID list, make sure that everything's good, and then when you stop, you can hit the stop button and then disconnect, and then go to log file and go to close log file, because what that will do is blow away all your data and start with a fresh page, because you don't want to sit in your driveway for 5 to 10 minutes screwing around with your graphs trying to get all your PIDs working and then take off and start recording values, because what you're going to be doing then is picking up a lot of garbage data from your driveway that you didn't want to be part of your scan. So start a new one at that point as soon as you leave and go for your actual drive, and then you'll be picking up mostly good data that's representative of how you would normally drive the car and not just idling in your driveway. So with all that said, that's pretty much how you set this up for your road scan. So the next step, of course, is to go out and connect your hardware and go for a drive. So let's wrap up here, and the next video that I make will be about the actual data collection and how to process it afterwards. We're going to go through how to interpret the data, how to format the data, and how to use it to actually correct your tables so that you have a much better fuel map, your VE table tuning and all that. We're not going to go through stuff that I went through in my previous video about which buttons to toggle or which settings to turn on or off. That's all part of basic tuning. I've gone over it in a previous video, and you can consult that video for those types of changes. But this is focusing very specifically on making your core table changes, like your fuel map and your spark table to some extent as well. But this is like the real tuning part that takes a lot of time and iteration and all of that. The other stuff is more like binary. You flip it on and or off, and it's set forever. But this is the stuff that you need to master if you want to be a good tuner and if you want to get your car in tip-top shape and keep it that way. Because especially with open loop, the numbers really shouldn't change over time. Like I said, they don't drift with a VE tune unless you make physical changes to your car. But having said that, you still want to make sure that you get it really dialed in well, and that does take considerable time, because these numbers are very sensitive. You have to make very small changes, and sometimes even if you need a 30%, sorry, that's a horrible number to pick. Sometimes even if you need a 5% change to a cell value, you don't want to actually make that 5% change all at once. You want to make it in steps, sometimes 1% at a time, so you can creep up on the actual perfect number, because overshooting will just mean more tuning for you, and you could diverge completely and make the number worse. So better to start small and work your way up and sneak up on it. So anyway, enough talking for now. I'll see you after we've done the car tuning, and we'll talk about the rest of the data collection and processing. So we're outside right now looking at my HPTuner module, and as I said, this is the Pro version that's got the green terminal block where my thumb is. And all that does is allow you to connect external sensors and log them as though you were logging an internal PID. Just adds extra physical channels. Now, I thought that this was better labeled, but it isn't. So I must have figured it out either by trial and error or using a multimeter. I can't remember, to be honest. So I thought it might be best to just show it to you, and that way you can just copy my example, and hopefully it'll work for you the same way that it did for me without having to go through the guesswork. So you can see the orientation of the unit, and you can see the position of the wires in the terminal block. The way that I've got mine laid out, I'm pretty sure, is that the red wire is the signal wire and the blue wire is ground, which, looking at it, seems counterintuitive because the blue wire is like right in the middle of the terminal block, and I can't figure out why they would choose that as ground, to be honest. But that seems to be the case. Although I have to say that in the software, I identify this as MPVI channel 1, and the red wire is connected to the first screw in the terminal block, so that could be channel 1 for all I know. I really don't know how they laid this out, but this is how I've got mine laid out. So I've got the red wire in the first position, skipped 3 of them, and then the blue ones in the 5th position, starting from the top of the unit. And then the red wire being the signal wire, that's going to connect to the signal wire that comes out of your AEM or whatever brand you have Wideband O2 sensor. So that Wideband O2 should have a diagnostic wire and a ground wire. You hook up the diagnostic signal wire to the red one and the ground wire to the blue one, and put them in the positions that you see here. And then when you go into HPTuners on the computer, you should be able to find it under channel 1. Piece of advice I would say is just to use some kind of shielding if you can for your wire. I mean, twisted pair is what I'm using here. You can see the twists in it, and that's twisted pair is good for canceling out like magnetic interference. Like if you've got high power noise from something that's using a lot of current nearby, and cars are very noisy, right? So they have a lot of sources of noise. That twisted pair will help keep your signal a little bit cleaner. But if you've got like shielded cable, coax, anything like that, anything fancy that you can break out into wires at the terminal block here and still connect it properly, go nuts. The better the signal, the better the wire, the better the signal is basically what I'm saying. But yeah, I just wanted to show you the layout here so that you understood how to connect this thing up so that you can use your wideband to do a proper open loop scan.